Hello everybody, welcome into another lesson. So today we are going to talk about infinite limits, and this is actually going to tie heavily into the lesson we did yesterday, which was one-sided limits. So infinite limits are if you have the limit as x approaches some constant a, the value of your function is going to take on either positive or negative infinity. So your answer is either going to end up being positive or negative infinity. This is not the same as limits at infinity. That's a different topic. A limit at infinity is going to be as x approaches positive or minus infinity. So that's a few lessons from now. We'll get into limits at infinity. But infinite limits are where your answer is positive or minus infinity. Now, there is a caveat with this. We're actually in a bit of a gray area when it comes to infinite limits. Technically, for a limit to exist, it has to converge to a finite number. So technically, the limit would not exist if you get positive or negative infinity. But I say it's a gray area because a lot of the time in calculus, when we're dealing with limits, especially when we want to understand the graphical behavior of a function, we're going to actually give an answer of positive or negative infinity almost as if the limit exists so we can understand the behavior of the curve. Now, a lot of professors are okay with that, but there are some professors that will say, no, you're going to say it does not exist. So ultimately, you need to follow what your professor's saying. So that's a bit of a disclaimer I must give you about that, is your professor may say to write, no, the limit does not exist. But the way I teach it, the way I was taught, and a lot of professors I know do this, is if you get an answer of positive or negative infinity, you're actually going to write that as your answer for the limit. Just so you can understand the behavior of the graph. Because if you say the limit doesn't exist, okay, well, why doesn't it exist? If you say the answer is infinity or negative infinity, that helps you understand the graphical behavior. Such as you have f of x equals 1 over x. Let's do this one real quick. So if I take the limit as x approaches 0 from the left of 1 over x, if I'm approaching 0 from the left of f of x equals 1 over x, I'm getting infinitely closer and closer to the x value of 0. I'm moving towards a value of negative infinity. It keeps getting infinitely and infinitely negative. So the limit as x approaches 0 from the left is going to be negative infinity. Now, what if I did it from the right? So I'll take the limit as x approaches 0 from the right of 1 over x. If I get infinitely closer and closer to x equals 0 from the right, my number is getting bigger and bigger. It's getting more positive. It's getting infinitely positive. So the limit as x approaches 0 from the right of 1 over x is positive infinity. Well, this again ties into one-sided limits. I'm going to write it up here. So if I want to now evaluate the limit as x approaches 0, in other words, the general limit of 1 over x, if we remember from yesterday's lesson, the left-handed limit must exist, the right-handed limit must exist, which for all intents and purposes, we're going to say these two limits exist. But the third criteria is that the left-handed limit must equal the right-handed limit. Well, negative infinity does not equal positive infinity, so the general limit as x approaches 0 of 1 over x does not exist. So the general limit would not exist, but you have a left-handed and right-handed limit. But there is that. And when are you likely to deal with infinite limits? You're very likely to deal with them in rational functions. They're always occurring in rational functions. Also in logarithmic functions. Let's do an example of a logarithmic function. We'll just do the classic f of x equals the natural log of x. Why don't we do that? So your logarithmic function's doing something like this, your natural log function. So there's your natural log function graph. Now notice as I approach x equals 0 from the right, if I take the limit as x approaches 0 from the right of the natural log of x, I'm getting more negative and negative. So as x approaches 0 from the right of the natural log of x, I'm going to negative infinity. Well, okay, what about the left-handed limit as x approaches 0 of the natural log of x? Well, for the natural log function, x is not defined for less than or equal to 0. So the left-handed limit of the natural log of x does not exist. So that limit does not even exist in that case. Now, if the limit doesn't even exist for the left-handed side, we can definitely say the general limit as x approaches 0 of the natural log of x does not exist. So that one was pretty easy. We've immediately shown that one of the conditions is violated to have the general limit exist, because a left-handed limit doesn't even exist. In fact, you may get some problems like prove the limit doesn't exist. That's incredibly easy. That's the easiest proof you'll ever do. In order to prove a limit doesn't exist, all you have to do is immediately show that one of the conditions is violated, such as a left-handed limit doesn't exist, the right-handed limit doesn't exist, or if they exist, that the left-handed limit doesn't equal the right-handed limit. That's all you have to show if you're ever asked to prove a limit doesn't exist. Now, to prove a limit does exist, on the other hand, that's much harder, and that'll tie into a lesson we're going to do about midweek when we get into the precise definition of a limit. That's probably the hardest topic of Calc 1. We'll get into that in midweek, but for now, we'll stick with what we're doing here. Now, what if I decided to make f of x equal to 1 over x squared? So f of x equals 1 over x squared. Let me just draw that real quick here. So there's the right-handed branch of f of x equals 1 over x squared. If we do the left branch of it, so there's f of x equals 1 over x squared. This time, let's take, once again, the left-handed limit. I'm going to erase that. If I take the left-handed limit as x approaches 0 of 1 over x squared, so I'm approaching x equals 0 from the left, I'm getting closer and closer to infinity. So this would actually be positive infinity. So what about the limit as x approaches 0 from the right of 1 over x squared? Well, as I continue to approach x equals 0 from the right infinitely closer, this is also converging to infinity. Writing these as infinity helps us to understand what the graph is doing as it approaches 0. This helps us get a clearer picture of the curve. Now, since the left-handed limit and the right-handed limit exist, for these intents and purposes at least, we can actually say the general limit in this case as x approaches 0 exists. The limit as x approaches 0, the general limit of 1 over x squared, would equal infinity, since the left-handed limit matches the right-handed limit. But again, your professor may say it doesn't exist because technically a limit has to converge to a finite number in order to exist. But most professors I know would say you would write infinity for your answer. Just so you know, it's going to vary by who your professor is. What else? Now, if for 4 out of the 6 trig functions, you're also going to have infinite limits. Sine and cosine don't have infinite limits because the range oscillates between -1 and +1. That's your range, -1 to +1 for both sine and cosine, but for the other 4 trig functions, you have infinite limits. So why don't we do the tangent of x? So we'll do f of x equals the tangent of x. So we know then at pi over 2, we'll make pi over 2 you know what? Because we're going to take the limit at pi over 2 of the tangent of x. That's what we're going to do. So here's, let's see, 3, 4, 5, there's pi, 6, 7.5, which would put me at 3 pi over 2. Okay. So I'm just going to do a little bit of graphing for the tangent of x. I'm not going to do 2 full periods. We want to take the limit as x approaches pi over 2 from the left of the tangent of x. So why don't we graph the tangent of x function? We know the tangent of x looks a lot like this. So there's your tangent of x function, and again we'll put it at pi here. We'll do another graph. There's your graph of the tangent of x function from negative pi over 2 to 3 pi over 2. You notice it just continues to do this infinitely. If I want to take the limit as x approaches pi over 2, which is right here from the left, I'm infinitely approaching pi over 2 from the left, I'm going towards positive infinity. So the limit as the x approaches pi over 2 from the left of the tangent of x goes towards infinity. Now you know what's coming next. The limit as x approaches pi over 2 from the right of the tangent of x. So let's get infinitely closer to x equals pi over 2 from the right. It's going down towards negative infinity. So the right-handed limit as x approaches pi over 2 of tangent of x is negative infinity. Now, since the left-handed limit does not match the right-handed limit, that means the general limit as x approaches pi over 2 of the tangent of x does not exist. So the general limit as x approaches pi over 2 of the tangent of x does not exist. Now let's do another trig function, because I'm not going to do cotangent because it's very similar to tangent. We have then also secant and cosecant functions. You would see this. Let's do the cosecant. I think we'll pick the cosecant. So we'll do f of x equals the cosecant of x. So yeah, f of x equals the cosecant of x. Let's graph this. I want to go towards pi. The limit as x approaches pi from the left of the cosecant of x, and the limit as x approaches pi from the right of the cosecant of x. So let's see, where are our asymptotes for the cosecant of x? It's going to be at integer multiples of pi. So at 0, then at pi itself, 1, 2, 3, 4, 5. Here's pi, that's a vertical asymptote. Forgive the nails on the chalkboard sound. And then again at 2 pi, it's the next one. That's your next asymptote. Okay. So here's going to be pi over 2. The cosecant of pi over 2 is going to be 1. We know the graph of the cosecant goes up like this. And then to the right of pi, so if we take the cosecant of 3 pi over 2, we're down at -1. The graph goes down like this. And it'll keep doing this infinitely for the cosecant of x. Well, here's the line x equals pi. That's an asymptote. If I approach x equals pi from the left, I get infinitely closer and closer to pi from the left. I'm going towards positive infinity. So the left-handed limit as x approaches pi of the cosecant of x is positive infinity. Now this time let's take the right-handed limit. If I approach x equals pi from the right, I get infinitely closer and closer. I'm going towards negative infinity. So those are these. You got two limits here. The left-handed limit goes towards infinity. The right-handed limit goes towards negative infinity. So that means we can say the general limit as x approaches pi of the cosecant of x does not exist. So the general limit as x approaches pi of the cosecant of x does not exist. So we've shown you examples here of when you're often going to see these infinite limits. Now let's dive into some problems here. We could even do that without graphing. So let's see. We're going to just take the right-handed limit. The limit as x approaches 5 from the right of 6 all over x minus 5. So what if you were asked to find the right-handed limit as x approaches 5 of 6 all over x minus 5? We have a rational function. So you're going to approach 5 from the right. Well, we definitely can't substitute in 5 itself because you would get 6 over 0, which is undefined. But think about 5 from the right. The number is going to be bigger than 5. It's going to be greater than 5. So if I put in 5.1, I'll have a positive denominator. If I put in 5.001, I would still have a positive denominator. Notice I am getting smaller and smaller values in the denominator, which is actually, when you divide by decimals, you invert and multiply that fraction, you're actually going to end up converging towards positive infinity. So the right-handed limit as x approaches 5 of 6 over x minus 5 would be positive infinity. Okay, now let's take the left-handed limit as x approaches 5 of 6 over x minus 5. So the limit as x approaches 5 from the left of 6 over x minus 5. Well, approaching 5 from the left, that means the number is going to be smaller than 5. So if I put in 4.9 for x, I'm going to get a negative value in the denominator. Let's say I put in 4.99, 4.999. I'm going to get some really small decimal numbers, which are going to be small fractions. But remember, when you divide by a fraction, you invert and multiply. So in reality, this is going to converge to negative infinity. So the left-handed limit as x approaches 5 of 6 over x minus 5 would equal negative infinity, which means then that the general limit as x approaches 5 of 6 over x minus 5 does not exist, because the right-handed limit and the left-handed limit don't match. So the general limit as x approaches 5 of 6 over x minus 5 does not exist. All right. Now we just have the limit as x approaches 1 of 2 minus x all over x minus 1 quantity squared. So we have the limit as x approaches 1 of 2 minus x all over x minus 1 quantity squared. Well, why aren't we taking a left-handed or right-handed limit? Well, let's even look at your numerator to start. It doesn't matter if I get infinitely closer and closer to 1 from the right or left, I'm still going to have a positive numerator, right? So that means my numerator would be positive. What about my denominator? Well, again, look at your denominator, it's to the second power. So even if I had a negative inside the parentheses, you square that, it turns positive. And definitely if you have a positive and you square it, it turns positive. If you're going to put in infinitely closer and closer values to 1 from either side, you're going to get infinitely smaller and smaller numbers in the denominator, and again, when you invert and multiply, this limit would converge to positive infinity. So we can actually say the general limit exists for this function. The limit as x approaches 1 of 2 minus x over x minus 1 squared is positive infinity. Sometimes it might help you to just put the signs in your numerator and denominator to figure out what your sign's going to be, whether it's going to be a positive or negative infinity. And of course, x minus 1, this goes back to pre-calc and algebra. If you have a denominator that would make, if you have an x value that would make the denominator 0, that's undefined, that's your vertical asymptote, right? You'd have a vertical asymptote at x equals 1, so that's where you determine your left-handed and right-handed limit as x approaches that value of the vertical asymptote. And in this case, since both numerator and denominator are positive, no matter which side you approach 1 from, then you could say the general limit actually exists, and it's positive infinity. Alright, let's do another. Let's take the limit as x approaches 0 of x minus 1 over x squared times x plus 2. So we got the limit as x approaches 0 of x minus 1 over the quantity of x squared times x plus 2. Let's really stop and take a look at this here. Now, let's figure out your signs. Approaching, because x equals 0 in the denominator would give you a denominator of 0. So this is a vertical asymptote of the function. You would actually have a second vertical asymptote at x equals -2, but they aren't asking you that limit. They're only asking you as x approaches 0. Well, it doesn't really matter whether I approach 0 from the left or right. If I approach 0 from the left or right in the numerator, we're subtracting 1 from that value. That's going to give me a negative numerator, right? I'll have a negative numerator. Well, whether it's negative or positive for that x squared, I'm going to get a positive number. Now, what about the x plus 2 component? Again, it doesn't matter if I approach x equals 0 from the left or right. I'm going to get a positive value for that x plus 2. So we have a negative over positive times a positive, which would turn into a negative over positive, which would give me a negative. A negative divided by a positive is a negative. So in the end, we're actually going to go towards negative infinity. That would be the limit as x approaches 0 of this function. I would get negative infinity. It doesn't matter if I go from the left or right. We could say the general limit as x approaches 0 of this function is negative infinity. All right. Now, let's take the limit as x approaches -2 from the right of x minus 1 over x squared times x plus 2. So we got the same function, but this time we're considering the vertical asymptote at x equals -2, because that would make the denominator 0, which would make this undefined. Well, okay. If I approach -2 from the right, I put that in the numerator, I'm definitely going to get a negative numerator, aren't I? Now, what about in my denominator? Well, it does, if I put a -2 from the right, I'm getting infinitely closer and closer to -2. I'm going to have -1 point something. If I square that, that's positive. And then if I put that quantity into x plus 2, -2 from the right is greater than -2, so that will give me a positive value for my x plus 2 quantity. I get yet another negative over a positive, which would give me a negative. So the limit as x approaches -2 from the right of this function would be -infinity. Alright, now let's switch it up. What about if we have the limit as x approaches -2 from the left of this function of x minus 1 over x squared times x plus 2. This time I want to go from the left. So if I approach -2 from the left, that means smaller than -2. I'd have -2 point something in the numerator. That's going to give me a negative numerator. Now, if I put that same value into the x squared, that would turn it positive. But let's say I pick a number less than -2 to put into the x plus 2 quantity. That's actually going to give me a negative. So I'm going to end up having a negative over a negative, which would turn this positive. So that means the limit as x approaches -2 from the left of this function is positive infinity. If we approach it from the right, it's negative infinity. So that means we could say the general limit as x approaches -2 of this particular function does not exist, because the left-handed limit does not match the right-handed limit. Alright, so that's how that ties into what we did in yesterday's lesson with the one-sided limits. Now, we're going to do a few exercises of proving a limit doesn't exist. And it's actually, as I said earlier, is probably the easiest proof you'll ever do in all of math. It's easier than anything we've done so far. So prove the limit does not exist. Okay. Let's recap this here. For the general limit to exist, so we want to talk about, for the general limit to exist, 1, the left-handed limit must exist. 2, the right-handed limit must exist. And then 3, the left-handed limit must equal the right-handed limit. If we're setting out to prove a limit does not exist, all we have to do is show that just one of these conditions is violated, and we've proven the limit doesn't exist. So let's prove the limit as x approaches 5 of the natural log of x minus 5 does not exist. So we're setting out to prove that the limit as x approaches 5 of the natural log of x minus 5 does not exist. Well, keep in mind this is the graph of the natural log of x shifted to the right 5 units. We have shifted this graph to the right 5 units. So you have a vertical asymptote at x equals 5. Well, why don't we do the left-handed limit here? Let me write in blue ink. Since this is the original problem, I'm going to do the proof. First, let's take the left-handed limit. So the limit as x approaches 5 from the left of the natural log of x minus 5. Well, if we approach 5 from the left, you're going to have a number less than 5. That's going to give you a negative value inside your parentheses. Remember, the natural log is not defined for numbers less than or equal to 0. So right away, the left-handed limit does not exist. we've immediately proven that this limit does not exist because the left-handed limit does not exist. Therefore, the limit as x approaches 5 of the natural log of x minus 5 does not exist. So we immediately can prove the general limit does not exist because the left-handed limit doesn't exist. Therefore, this limit does not exist. That's the extent of your proof. All you have to do is show that one of these three conditions is violated, and you've just proven the limit doesn't exist. Let's do another one here. So what if I take... Alright, so let's take the limit as x approaches pi over 2 of the secant of x. So we're going to prove the limit as x approaches pi over 2 of the secant of x does not exist. Well, we know that odd multiples of pi over 2 are your asymptotes for the secant function, right? You got pi over 2, negative pi over 2, 3 pi over 2. All those are asymptotes for your secant function, meaning it's undefined there. Well, first thing you want to do, take the left-handed limit as x approaches pi over 2 from the left. As x approaches pi over 2 from the left of the secant of x, picture your graph. Pi over 2 from the left is going to be smaller than pi over 2, meaning it's in the first quadrant. So this is going to be in the first quadrant, meaning that you're actually then going to have positive infinity. If we picture the graph of the secant of x, and maybe it helps you to draw a graph, you're going to get positive infinity for your left-handed limit of the secant of x. Now, let's say I take the right-handed limit as x approaches pi over 2 from the right of the secant of x greater than pi over 2, since it's from the right, would mean you're approaching pi over 2 from the second quadrant. Well, that's going to go towards negative infinity, because if you're in the second quadrant, your secant's negative. So the left-handed limit is positive infinity, the right-handed limit's negative infinity. Now, both limits exist, but the left-handed limit does not equal the right-handed limit. We have proven that condition 3 is violated. The left-handed limit does not equal the right-handed limit. Therefore, the limit as x approaches pi over 2 of the secant of x does not exist, because the left-handed limit does not equal the right-handed limit. Okay, let's do one more. And I think we'll also do a trig function. Let's take the limit as x approaches 2 pi of the cotangent of x. So we're going to prove that the limit as x approaches 2 pi of the cotangent of x does not exist. So integer multiples of pi, of course, are your asymptotes for the cotangent function. You have 0, pi, 2 pi, negative 2 pi, so on. Those are your vertical asymptotes for the cotangent of x. Well, let's approach pi over 2 from the left. So take your left-handed limit as x approaches 2 pi from the left of the cotangent of x. Well, that's going to put you down in the fourth quadrant. If you're approaching 2 pi from the left, you got a value less than 2 pi. That's going to put you in the fourth quadrant, which is going to give you negative infinity. So the limit as x approaches 2 pi from the left of the cotangent of x is negative infinity. What about then, let's take the right-handed limit as x approaches 2 pi from the right of the cotangent of x. Well, if you're approaching 2 pi from the right, that means it's going to be greater than 2 pi. That would put you back in the first quadrant, which would give you a positive cotangent. So the right-handed limit as x approaches 2 pi of the cotangent of x is positive infinity. Well, we can show that the left-handed limit does not equal the right-handed limit because negative infinity does not equal positive infinity. So we're going to say the left-handed limit does not equal the right-handed limit. Therefore, the limit as x approaches 2 pi of the cotangent of x does not exist. We have shown that condition 3 is violated. The left-handed limit does not equal the right-handed limit, so therefore the limit as x approaches 2 pi of the cotangent of x does not exist. Alright, so that's it for this lesson. The next lesson we're going to talk about some limit laws that are actually going to make our lives a lot easier for evaluating limits. And then the lesson after that we'll actually learn methods for evaluating limits. But we're going to do some limit laws in the next lesson, such as when you have addition of limits, subtraction, multiplication, division, limits to powers, so on, and constants times limits. We'll learn some rules for that. So I hope everybody has a great day. Take care.